This video is about alkene stability, which is related to E1 and E2 regiochemistry and also stereochemistry. In section 9.10 in the Carty book, this will be on page 488. There's a little section about this, and the biggest thing we need to memorize effectively is the relative stability of the alkenes. Thankfully, this follows a similar rule as the stability of carbocations and also the stability of radicals. So we already know that if we're looking at a carbocation, our methyl is going to be the least stable. Our primary will be the next most stable, or the next to the least stable, I should say. The secondary with 2 carbon atoms attached. And these don't have to be methyl groups, of course. They can be larger groups, but they do need to be carbon groups. And then tertiary being the most stable in this particular series here. All right, so this is the most stable. This is also the least substituted. And by substituted, I mean that there are, well, in this case, no carbon atoms substituted for hydrogen atoms. This is the most substituted, with all of the potential hydrogen atoms being substituted with carbon atoms. Okay, and this follows the same pattern for radicals. So, for example, if these were radicals instead of carbocations, we would have 1 unpaired electron on each of these. And the tertiary would be the most stable, and the methyl would be the least stable. We haven't really talked about any of these reactions in this semester. We'll talk a little bit about radical reactions in organic too. But the bottom line remains that the most stable is the most substituted. So that's going to actually follow here with the alkenes. And here we're looking at how many of the potential hydrogen atoms that would be bonded to the vinylic carbon atoms are substituted. Let me just draw the bond line structures instead. I think that'll be easier. Or mostly bond line, I suppose. So here, if these are all 3 methyl groups or some sort of R group, then this is going to be called tetrasubstituted. And this is going to be the most stable. The next most stable would be trisubstituted. And again, these don't have to be methyl groups. I'm just drawing methyl groups here as a example. They could be larger groups. And then with disubstituted, it does get a little complicated because we have 3 ways that an alkene could be disubstituted. One way is that one of the vinylic carbon atoms has 2 alkyl groups on it and the other one has none. So this would be the next most stable. And then the next most stable would be the trans substituted on the 2 different carbon atoms. So this is disubstituted with both of the carbon atoms on the same carbon, and then trans disubstituted. And then the next one would be cis disubstituted. And it makes sense here that the trans group groups have more space around them, whereas the cis groups, especially if they get to be larger groups, this is going to be more steric hindrance here. They're going to start to literally bump into each other. So the cis disubstituted is less stable than the trans. So this is important to remember here. That's usually more likely to come up than the disubstituted, as a point of difference anyway, than the disubstituted with the two carbon atoms, with the two alkyl groups on the same vinylic atom. Next, we'll have monosubstituted, which would be one carbon group present on one of the vinylic carbon atoms. And then the least stable would be unsubstituted, which would just be ethane, acetylene. Goodness, ethylene. So this would be the unsubstituted. All right, so this is the most stable, and this is the least stable. And where this is going to come up is when you're trying to determine which is the most favorable product. So this is thermodynamic stability. So let's just look at an example here of an alkene with, or a product, a substrate that can do an elimination reaction with some different substitution patterns here. So here's a good example where, let's see, I'm going to put, I'll put the leaving group here. So we'll make it a chloride leaving group. And I'm just going to use a generic base in this instance and not specify the base. But if we look at this here, we have one alpha carbon, but then we have 3 unique beta carbon atoms. And so we have 3 possibilities here for the different products that could form. I haven't specified stereochemistry at this carbon. This carbon would be, this beta carbon here, would be would be a chirality center. But I'm trying not to muddy the water too much. So let's just look at, this is called regiochemistry. So regiochemistry means basically where the bonds will form, or where the reaction is going to happen. Regio, I remember this because regio sounds like region, which is the different areas. Usually we think about that geographically, but here we're thinking about it within the structure. So what I'm going to do is I'm going to use a few different colors here. So if I remove the methyl beta here, then that product would look like this. And this would be disubstituted with both of the R groups being on the same vinylic carbon atom. So technically this would be more stable than a cis or trans setup. Okay, let's look at another color here. We'll use green. Okay, so if we're removing the green beta hydrogen atom, then we're going to end up with the double bond being here. Okay, so now I have a tri-substituted product. Now, technically here, I could make 2 different stereoisomers. So let me go ahead and draw both the stereoisomers because I have two different hydrogen atoms here that could be taken. So I'll draw the other tri-substituted stereoisomer, which would look like this. But hopefully if we're looking at this, we're recognizing that here we have an H atom with this bulkier group. And then we've got the two methyls here. On this one, though, we have a methyl group with this bulkier group. So that's going to be less favorable. So if I'm really trying to determine the most stable, then I'm going to say that this is going to be most likely a minor product. And I might not even draw it because it's going to be less favorable than this stereoisomer here. Okay, so the last possible product, let's see, we'll use this kind of light blue color, is that we could take a hydrogen atom off of that beta carbon. And if we take a hydrogen atom off of that beta carbon, and again here, this one would be a stereospecific, where if I had given you the wedge or the dash, you would have to rotate things and set it up in the proper geometry with the anti-periplanar setup for the H and the Cl. But I didn't. I'm trying to keep it simple. So I'm just going to draw a product, a stereoisomer, and know that it would be a single stereoisomer that we would get here. Okay, so this one is tetrasubstituted. Okay, so if we're looking at these, this one is going to be the most stable thermodynamically. Then this would be like the middle stability. And then this one would be the least stable. So a little bit of this would depend upon which mechanism was present as to which product would be formed, and also which base is present. So here, for this particular one, if this reaction were going E1, I'm going to label these product A, product B, product C. Then the major product would definitely be product A. And then you might have a little bit of B, and then the di-substituted and the other stereoisomer of the minor of the tri-substituted would be much, much smaller amounts. If you were asked to draw all the possible products, though, you would want to draw all four of these. But most of the time what we're being asked is what is the major product. So the major product here would be A. Now, if this is E2, it will depend upon the base that is present. So if it is a smaller base, then we're much more likely to get product A. And by small base, I usually mean like hydroxide, methoxide, ethoxide, one of those where you don't have a bunch of substitution. If you have a large base, and usually the large bases that we use are potassium tertbutoxide, KOT-bu, which is going to be very bulky, or LDA, which is lithium diisopropyl amide. And those are going to be more likely to take from the less substituted hydrogen because it would be harder for a larger bulky base to get in here into this beta carbon atom that's a little more sterically hindered, or a lot more sterically hindered in this case. And it's going to be easier for these bulky bases to get to maybe this one or particularly this one. And so you tend to get the less thermodynamically stable product when you have a large base. Usually, we don't have this quite of a complicated reaction where, usually it's just one is more substituted and one is less substituted. When we have the more substituted, it's usually called the Zaitsev product. And that's the one we're going to get if we have a small base present. And then the less substituted one, which is less thermodynamically stable, is called the Hoffman product. And it's going to be the one that's going to be formed if you have one of the larger bases present. We would get product C in this instance. Now for E1, it is possible to get the less thermodynamically stable one, the less substituted one. Typically, that's only going to happen if you have, again, a larger base, or sometimes for E1 if the substrate is very bulky. So here we can get maybe C if the substrate is bulky. And there's an experiment in the lab we've done in the past where that happens. We get more Hoffman than Zaitsev, more of the less thermodynamically stable. And it's an E1 mechanism, but that is less likely to occur. And so usually with E1, we're going to assume that we're going to get the Zaitsev, unless there's something in particular going on.